talk. Okay, so today I'll give introduction and also literature overview and what we have worked on spoken language understanding. So the title of the talk is Transfer Learning for End-to-End Spoken Language Understanding. And here is my email address. So if anyone is interested to need any resource or do same kind of research, they can contact me in the same email address. Okay, so this is the outline of the talk. First, I'll introduce what is spoken language understanding and what is intent classification. Then we will see how people have approached the problem in the literature. And then we will go to our, we have done some work in the last 2 years using knowledge distillation or transfer learning. We will learn that, and then we will see how we can do knowledge distillation in a transformer-based model. So the spoken language understanding area focus on deriving meaningful interpretation of a spoken utterance. And meaningful interpretation means extracting the semantics from the spoken utterance. Semantics, the example of semantics are slot filling, intent classification, domain classification, dialogue act classification, etc. And intent classification is a major part of, play a great role in the spoken language understanding domain. Because based on so with the recent increase in mobile devices or any voice operated interfaces, we talk to for example Alexa or Siri, we talk to them through spoken form, right? And the same voice interface reply to us based on our question. So the first thing they do is they recognize our intent. Suppose we say play the song, then they recognize what is the meaning of our the spoken utterance. Is it playing a song or switching off the light? What is the task we are giving to them through the speech signal or spoken utterance? So that is called as intent, the meaning or intention of the spoken utterance spoken by the user to the voice interface or any other robotic setup. So you all are familiar with, I think, the voice operated interfaces or the chatbot. The intent classification or spoken language understanding has a major role in voice operated interfaces and also in chatbot. Usually the spoken language understanding system or intent classification system, let's say it intent classification because I'll specifically focused on intent, but the same can be applied to any task in spoken language understanding. Usually we do a pipeline approach. The pipeline approach means we have two components. One is the automatic speech recognition engine and another is the natural language understanding module. Suppose we have a speech signal spoken by a user. The ASR, automatic speech recognition, first convert it to text form, and then the text is passed through the natural language understanding module, which detects the intent or slot or other semantics from the text. This is the conventional pipeline approach that has been used in all the most of the applications currently. But this approach has some limitations. Let's speak about the first limitation. As we know, we always train or optimize ASR system to reduce the word error rate. That means we train the automatic speech recognition module to correctly convert speech to text. We don't care about intent or slot or any other spoken language understanding based semantics. And the NLU component is trained entirely to get the intent or slot or other semantics from the text. And both the modules are optimized separately. So that is the first disadvantage, that we don't optimize them jointly, and it is in the practical situation, it is not possible to optimize jointly, because joint optimization and of ASR and NLU requires a huge database. Again, in some conditions, suppose in a noisy environment, the ASR may not work well. The ASR is trained on certain domain, and we are applying it to some other domain, and then the ASR may give us wrong transcription as well. But the natural language understanding module is always trained on correct text or on ground truth text to predict the intent. So in that case, if the text or transcription derived from the ASR is erroneous, then the NLU component will not work properly to derive the intent of a sentence. So that is one problem. Another problem with this kind of framework is the underlying motivation for this framework. And as we know that when we speak a sentence, we emphasize on certain words, right? We do not speak all the words in the sentence with the same level of energy or with the same intensity. Some words carry more information towards the meaning of the utterance, whereas some words are not that important to understand the sentence. And in this kind of framework, as we are predicting the intent from the text, we are not considering the intensity or the energy level or the pitch variation we are putting into the sentence to convey the meaning better to the listener. So these informations like pitch, duration, and energy is called prosodic information, and these informations are not incorporated in this pipeline approach. So one of the solution to these problems is the end-to-end approach. As we know that in different domains like speech translation or in speech recognition and speech synthesis, the end-to-end approaches have shown like progress pretty much, and they have been very successful. So, so if we are able to develop an end-to-end system where we can directly feed the speech signal and derive the intents from the speech signal without any intermediate automatic speech recognition or natural language understanding modules, then we think that it would be more beneficial, and it would require less effort. Along with that, we know we have already told that human perception of a spoken utterance depends on both the acoustic and linguistic information. Like the text also convey us some information, and the spoken form also convey us some information to understand the meaning. So in the end-to-end approach, if we use the speech signal, so speech signal has two information. One is the acoustic information, which is the prosodic information, and along with that, it has the linguistic information as well. So if we use the entire speech signal and then use it for intent classification, we may be able to incorporate both prosodic and linguistic information into our spoken language understanding systems. So in the reference, there are some initial works done in this direction in the spoken language understanding field. So if we say about the approaches in the literature, the end-to-end approaches, the first thing comes to our mind is we can extract some acoustic features from the speech signal and use a classification network to classify the intent. So that is a very straightforward method. Next, we can also do a multitask learning method where we can learn the text and semantics using the same network. And then we can, thirdly, we can use pre-trained acoustic model or pre-trained language model or any pre-trained resource for the end-to-end spoken language understanding. And next, we can use a knowledge distillation or transfer learning that we will speak in details in the later. spoken language understanding. So basically these four are the different directions that we can go for developing a end-to-end spoken language understanding system. So to directly map acoustic features to intent, domain, or any SLU task, we can use a feature extractor. We can use any feature extractor where the features are very meaningful for the task. And these features can be used in a classification network for the corresponding intent or domain classification. So this kind of work has been done in these references in the literature, and they are not quite successful because they could not get very high accuracy because of limited data available for the task. Then what we can do is we can use a multitask model. So this work is from Google in 2018. They have shown different kind of end-to-end models that has possibility in end-to-end SLU. So firstly, they do a encoder-decoder model, which is same as the previous slide I just showed. And next, they have a joint model where they have an encoder to encode the speech signal, and they have a decoder where with the same decoder they do these W are the words of the sentence. In these S variables are the semantics of the sentence. So they predict both words and semantics with the same decoder. Thirdly, they tried a multitask model where they have an encoder and they have two separate decoders. One decoder is for predicting the words in the sentence, and another decoder is to predict the semantics. Semantics means intent or slots or other spoken language understanding tasks. And then they have a multi-stage model where they have two stages. One stage is to predict the words from a spoken utterance, and the next stage is to predict the semantics. So among all these, they found that they trained these systems using like 24 million English utterances, which is a very, very huge database. And there they found that the multitask method have the best performance. But the problem here is they have used a database of 24 million English utterances, and those are annotated with the semantics and the words, and they have speech signals also. But for us or for the research community, it is not possible to get such a large database. So although this method gives very good performance, but they have a they have the limitation of using a very large database. So to overcome this problem of requirement of a very large database, in the next few publications, people have tried to use pre-trained resource. So if we have a pre-trained model like pre-trained acoustic model or pre-trained linguistic model, which is trained using a very large database, but not for the intent classification task, but we can use the knowledge from the pre-trained model and use in our intent classification network. So in this work highlighted here, they have used the pre-trained ASR model to extract the acoustic features from the speech signal, and they use those acoustic features or embeddings extracted from a pre-trained ASR model in the classification network. Yeah, so this is one kind of approach, and the next approach is knowledge distillation or transfer learning for speech to intent classification. And we worked in this direction for for using less data and for using both acoustic and linguistic information for intent classification. So as I already told in the previous slides, that our perception and interpretation of a spoken utterance requires both the prosodic and linguistic information. And we can we can leverage on information extracted from pre-trained acoustic and pre-trained language model to improve our acoustic and linguistic representations. And recently, not very recently, but from long time, the teacher-student networks or transfer learning methods have shown efficacy in different areas where we have a very less database, but we can use another teacher model, and we can get the knowledge from that model to train the student model for the targeted task. So in this approach, we have used such kind of teacher-student network or knowledge distillation method. So I'll first go to the components that we have used in the framework. Firstly, we use two pre-trained models. First is the pre-trained ASR model and a fine-tuned BERT model. So pre-trained ASR model is a acoustic model and BERT is a linguistic model, which is trained on huge text corpus. People whoever working on natural language understanding on NLP, they use the BERT model very often. We derive acoustic embeddings from the pre-trained ASR model, and we derive linguistic embeddings from the fine-tuned BERT model. And in this work, we use a transfer learning layer or knowledge distillation. And there we derive closer linguistic embeddings to the pre-trained BERT model using knowledge distillation. And then we use a strategy like cross-attention for combining these acoustic and linguistic embeddings. And another important point to note that is that we do not use any ASR in this, although there is a pre-trained ASR model that is used as a feature extractor, but we do not use any intermediate ASR model to derive the transcription or during the testing as well. We need to give only the speech as input, and the system will give us the semantics as output. So let's speak about how we have used the pre-trained ASR model. This pre-trained ASR model shown here in the left side of the figure is consists of a stack of neural networks where we have the input speech signal, and the first layer is trained to predict the phonemes of the training data. And there is a phoneme classifier, and then after this layer we have a word, we have another layer which followed by which we have a word classifier. So the entire ASR engine is trained to reduce the optimized on the combined word classification loss and phoneme classification loss. So this ASR is trained on LibriSpeech data, which is a very well-known database in the field of ASR. And after the ASR engine ASR is trained, we discard the word classifier and phoneme classifier layers, and then we take the embeddings from the intermediate layers. From these word classifier layers, we take the embeddings, and we call these embeddings in our work as acoustic embeddings, and these embeddings will be later used for intent classification. So if you see in the right side, once the ASR engine is trained, we have we use those in the top layer for intent classification. And I already told that this is trained using LibriSpeech data, and we use the word and phonemes as targets. And the output sequence of hidden representations represent the phonetic content, and we derive 256 dimensional acoustic embeddings, which represents as like with this symbol from this pre-trained ASR model. So this pre-trained ASR model is a publicly available model. You can get the link in this paper. So they have released the ASR model, and we can directly use it without further training. And another pre-trained model we use is a pre-trained BERT model. We know that BERT model has been very successfully used in the sentence classification task or other NLP task. So with that note, we use the BERT model, but we can replace the BERT by any language, other language model. So in this case, we fine-tuned the pre-trained BERT model based on the evidences found in the literature. And for fine-tuning, we used a two-stage approach. First, we fine-tuned the BERT model for masked language model task with language model heads. And then we fine-tune it for intent classification labels as target. And from BERT, we get a sequential output of 768 dimension, and the sequence length depends on the length of the input utterance, and we do a mean pooling to get the exactly 768 into one dimensional vector from the pre-trained BERT model. And another thing to mention here is, although we have fine-tuned this model for on our database, the BERT model, but later we found that it performs same even though we do not fine-tune. So I think for future use, we do not need to fine-tune the BERT model for such a task. We can directly use the BERT model to extract the embeddings from the text sequence. So this is how the network looked like that we designed for the spoken language understanding. We call this network as acoustic-linguistic network with transfer learning, because we use both acoustic and linguistic information. And here our aim is to, although we are saying we are using both acoustic and linguistic information, but the linguistic information we are using is not directly extracted from text during the testing time or inference time. It is a learned linguistic representation or embeddings learned using the transfer learning layer. So to describe the framework, I'll first say that we have two models. One is pre-trained ASR model, and one is fine-tuned BERT model that I have already talked about in the last slides. And these two models are freezed. These two models are used only as feature extractors. They are not getting trained during the training of the network. Firstly, we have the speech signal, and we have the corresponding text as well in our training database. The speech signal is first passed through the pre-trained ASR model to derive the acoustic embeddings, and the text is passed through the fine-tuned BERT model to derive the linguistic embeddings. And using the transfer learning layer, we try to map the latent space of these acoustic embeddings towards the latent space of the linguistic embeddings. Transfer learning layer is a linear layer that transforms the 256 dimensional acoustic embeddings to 768 dimensional linguistic embeddings. And during this transformation, we have a teacher-student kind of network that we will speak later. And once we have the transformed linguistic embeddings and actual acoustic embeddings, we fuse both with a cross-attention layer. And once we have the fusion, we pass it to the intent classification layer, which is the task is only classification from the fused embeddings. And we train the entire model using two losses. One is the intent classification loss, definitely, because that is our target. And another is during the transfer learning method, learning, we take the mean square error loss between the linguistic embedding and the BERT linguistic embeddings derived from the acoustic embeddings and the BERT embeddings. So these two losses are weighted and combined, weighted and combined, and then used it for the backpropagation of the entire framework. So if we say specifically regarding the transfer learning layer, I already told with respect to the transfer learning layer, we have the teacher model, which is the BERT model, and we have the student model. Student layer is the transfer learning layer and teacher layer is the BERT layer. And this transfer learning layer transforms text input acoustic embeddings and outputs the linguistic embeddings. And during the training, we considered a loss between the output linguistic embeddings and the original BERT embeddings. So the focus of this is we are trying to derive the BERT-like embeddings from the acoustic embeddings. We are trying to transform the acoustic embeddings to BERT-like linguistic embeddings through the transfer learning layer. And if we visualize how we are, what we are achieving, or is it successful to convert the acoustic embeddings towards the BERT-like linguistic embeddings, we can visualize it in this figure. This is the TSNE visualization, where the red color is the BERT embeddings. If we plot for 6 intent classes, we can see different clusters of the BERT embeddings. But if we can see that the linguistic embeddings are in the, like, the linguistic embeddings means the output of the transfer learning layer is in the same cluster. Whatever is the intent classes, it doesn't have any information. But this is in the first epoch. Then after few epochs, or towards the final epoch, this transfer learning layer is able to make these linguistic embeddings behave similar as the BERT embeddings, and those are able to classify the 6 intent classes. And then after that, we have fused the acoustic and linguistic embeddings. And we can see here that we have the acoustic embeddings for different 6 intent classes, and we have the linguistic embeddings for 6 intent classes. And the linguistic embeddings works better than acoustic embeddings. But after fusion of both acoustic and linguistic embeddings, the clusters are far apart from each other, and those are able to better classify the intents. And this fusion that I have shown just now, that we fuse speech and text, is achieved through a cross attention layer. Cross attention is performed to align the acoustic and linguistic embeddings. We generate the alignment. As we know, the attention method in the transformer architecture, there are 3 components as input, query, key, and value. And based on the similarity between the query and key component, the value component is weighted. So here we have the query as acoustic embeddings as query, and predicted linguistic embeddings, or not predicted, transform linguistic embeddings as key and value components. And then we use this cross attention function to derive the alignment between the acoustic and linguistic embeddings. And this is the how it works is it first looks into the similarity between the acoustic and linguistic embeddings, and based on that similarity, it weights the linguistic embeddings, and that is how both the embeddings are fused. So the fused output is represented here by a variable z. Then we pass the fused output to the intent layer. So intent layer consists of some RNN layers, and then a linear max pooling and a linear classifier to classify the intents. And intent classification loss is a cross entropy loss, which is referred to as loss intent. And as we learned earlier, that transfer learning loss, which is loss TL, is the mean square error loss. So we have a variable alpha, and we weight both the losses according to the alpha value, and then we find the total loss of the network. And all these layers, which are in blue color, are optimized using the total loss. So to validate the idea, we need a database. We use two databases. Firstly, the ATIS database, which is the Air Traffic Information System data. So the ATIS database looks like this. Suppose the user asks the agent of the air traffic information how many of Delta flights are first class. That means the agent or the agent is not a human being. Agent is a system, and they understand that they are asking about quantity, that how many of Delta's night flights are in the first class. So that is about asking about a quantity or quantity of flights. So they mark this intent as ATIS quantity. And then if some other user asks how far is the airport from San Francisco, they mark it as distance, because the user is asking about distance of one place from another, and this intent is ATIS distance. So the next data we use is the fluent speech commands database. This database is developed for the home-based virtual assistant that can turn on, turn off the lights, or turn on, turn off the music, lower the volume of the music. So one example is turn the lights on in the kitchen. So in this case, there are different slots, which are action, object, and locations. Activate lights kitchen, and this is the intent, which is a combination of the slots. So this ATIS database is very long-standing database in the field of NLU, and fluent speech commands is proposed in 2019. And fluent speech commands is very widely used now because it is one of the large database that is present, which is freely available for research. And for experiments, we first train a ground truth system which use the original text. This is basically an NLP based system which use the ground truth text, not ASR output, and the BART based natural language understanding system. And then we develop a conventional pipeline approach that I have discussed in the first 2-3 slides. Which is ASR followed by natural language understanding. And then we have a pre-trained ASR model without transfer learning, where we directly extract the embeddings from the pre-trained ASR model and use it for classification. Then we have another model which used only linguistic embeddings from our network. And finally, we call it as ALN, which use the output of the cross-attention layer. And for the ground truths, we have these performances. Fluent speech commands database is an easy database, so the performance of the ground, like baseline itself is very high, like 98.8. And this table in the right side shows our work, that in the fluent speech commands as well, we get 99% of accuracy, and in the ATIS database we get 90.86, around 91% accuracy using the proposed method. And here we use different alpha values, and we found that if we put more emphasis on the transfer learning loss, the result is better. So yeah, so this was about the intent classification based on a transfer learning method. But in this case, we use a single language database for our work. But mostly current applications demands either bilingual or multilingual scenario or multilingual databases. So we did the same experiments on a multilingual setup. We just replaced the BERT model by a MBERT model, which is the multilingual version of the BERT model, and keeping all other modules same. So how we derive a multilingual database? We do not have any multilingual database in this domain, which has the speech signal and the semantics annotated in the which is available for us. So we created it for English and Mandarin. We have the English sentences from the Fluent Speech Commands database, and we automatically translate using Google Translator to Mandarin or Chinese. And then we use the Mandarin listeners to listen and manually correct it. That is a two-stage data preparation. And then we record these Mandarin utterances by several users, and we also synthesize using a multilingual text-to-speech synthesis system. In the text-to-speech synthesis system, we have 50 Mandarin speakers and 50 English speakers. So we synthesize both the English and Mandarin utterances for all the 50 Mandarin and 50 English speakers, and we created a synthesized version of the database, because getting a real huge database is not trivial and could not be done in very less time. Although we have the real database as well, which is a smaller version. So in this case, what we did is we did the same network, which is a proposed method and the baseline method for only English, only Mandarin, English, Mandarin, all the settings. And we found that using the proposed method, even in the multilingual case, the transfer learning works better compared to the one with, which is without transfer learning. And this gave us the a summary that the transfer learning method, or the idea of using pre-trained resources in acoustic and linguistic domain, helps us to derive a better model even using less database, even in the multilingual scenario or monolingual scenario. Okay. So so after finding this kind of method helpful, we thought that how can we improve the transfer learning strategy or the transfer learning method. The transfer learning strategy could be improved if we have a similar structured teacher layer, teacher model, and similar structure student model. Currently, in our framework, the teacher model is a BERT model, which is a transformer-based model, which consists of several transformer encoders. And the student model has this linear transfer learning layer, then cross attention, and then intent layer. The structure of the student and teacher layer is completely different for our case. So yeah, so what about if we replace the student model by the same transformer encoder, which has similar structure as the BERT model? Can it improve the transfer learning process? So we did replace the student model with a speech transformer encoder. The speech transformer models have three components. One, firstly, embeddings. embedding layer, encoder or embedding layer, and then secondly the encoder, and thirdly the decoder. But in this case, as the BART model consists of only the transformer encoders, we also use only the transformer encoder model for our student model. And the encoder model has two components, the multi-head attention and the feed-forward networks. And our student model consists of several, any number of such encoders. And this speech transformer encoder also leverage on the self-attention mechanism. And as we told that all the words in a sentence are not equally important to emphasize or to understand the meaning of the utterance. So some words are more important to understand the meaning. And this transformer architecture allows us to transform the audio frames into various subspaces, and then use the most relevant frames and weight the more relevant frames for the downstream task. And it allows us to extract the semantic context implied by an utterance. So this method we call as speech transformer distillation method, where the components are like, we have a pre-trained ASR model, we have a pre-trained BART model, we have a speech transformer encoder, and we have transformer to transformer knowledge distillation. So the pre-trained ASR model and pre-trained BART model are the same as what we used earlier, and the speech transformer and the pre-trained BART model is a teacher model, and the speech transformer encoder is a student model. And then in the transformer to transformer distillation, here we are doing two kind of distillation, because in the inside the transformer we have the feed forward networks and the multi-head attention. So we get the attention metrics from the multi-head attention, and we get the hidden metrics from the feed forward network. We have two metrics, and similarly from the BART model as well, we have the attention and the hidden metrics. And that's why we calculate the loss between the student attention and teacher attention, and we calculate the loss between the student hidden and the teacher hidden embeddings. Student is this transformer, and the teacher is the BART model. And we have the intent loss, because intent is the final target, and there we use cross entropy loss. And we weight these losses by some parameters based on their importance, and then we calculate the total loss, which is used to optimize the entire network. So this is how the speech transformer distillation model architecture looks like. So in the right side, so this is the model in figure A, and in the right side we have the teacher model, where all the layers are marked as with red color, and those are the free layers, those are the weights are not getting updated. And in the right side we have the student models, where we have different layers, and these layers are getting trained during training of the model. Once we have the teacher model and student model, we do the distillation, layer by layer distillation between the teacher and student model. Suppose layer 1 of the student model is learned from layer 3 of the student model, teacher model, with the hidden and attention loss that I have shown. And the last layer, suppose between these two layers, the loss is calculated and the knowledge is distilled from the teacher layer to the student layer. And inside each pair of layers, we have this structure, the multi-head attention and the feed-forward neural network, from where we extract the hidden and the attention metrics. And this looks little complicated, but in the figure, but this is a very straightforward transfer learning method from transformer teacher model to transformer based student model. And we have the loss total using which we optimize the entire model. For the BERT model, there are 12 layers, and for the student model, speech transformer encoder, we use 4 layers because this works optimally, and that this work best actually for 4 layers. So yeah, so here also we develop the baselines like earlier. We have the pre-trained ASR model, and we compare with this, and then secondly we have, without the distillation, only speech transformer model based spoken language understanding. And then we have the proposed method where we do only hidden embeddings distillation, not the embeddings distillation. And in the proposed method, we do both hidden and attention based distillation, where we have 3 kind of losses. And we found again the proposed method works better. But if we compare this framework with our earlier method that didn't use the transformer based distillation, in the 80s database, the earlier method worked better actually, which was 90%. But later we found that even in the noisy case, suppose we mix the speech signal with a little bit of noise, then also this distillation, transformer based distillation method is robust to that, and it is able to do the classification, but the earlier method failed. I think that result is not included in the slides. Yeah, so yeah, that's it. We have discussed 2 frameworks, mainly the transformer based knowledge distillation or transfer learning, and another one is the acoustic linguistic network, which is the normal transfer learning between the BERT based model and another student model for end-to-end intent classification. Yeah, so we learned that fusion of acoustic and linguistic embeddings effectively through cross attention works better, and we evaluate the same in a multilingual scenario. And you have seen that transformer to transformer knowledge distillation is also beneficial. And another thing I want to mention is, although we do not have a very big database, for people who are working in this area, they may know that if we want to develop a end-to-end intent classification or an end-to-end SLU model, there is scarcity of data, because such end-to-end models, like for suppose for ASR end-to-end research, it is a very matured area, and they have like thousands of hours of databases across different domains like that. But for SLU or spoken language understanding, we don't have that much database available. So in all the recent works or wherever we try to improve, we need to improve through transfer learning or knowledge distillation, and we need to use the pre-trained models, which are pre-trained for ASR task, for maybe the self-supervised models, recently the wave-to-wake models, uh, those models. We need to rely on those models, and we can use transfer learning technique to get some information from those models to our SLU network, and that has been quite successful. And I think that is that is the future in spoken language understanding without using very huge database. Yeah, and to say about the future directions, it is always beneficial if we put effort for data collection for a more robust model. And there is much scope to work in multilingual intent classification, multilingual end-to-end intent classification. And also in the multimodal study, what if currently we are using only audio and text for intent classification? What if we use audio, text, and visual cues as well based on the application for understanding the meaning, to get the facial expression of the speaker, and from that also we can help, we can get some aspects of the meaning of the sentence, and that is helpful in robotic setup. And there is also much scope to study in the far field scenario. Currently, whatever data we use is all are spoken through, recorded through headphone. But when we speak to a robot, we or a virtual assistant as well, we can speak from a certain distance, or we can speak from different angles. So in that case, optimization of both speech localization or speaker localization with the intent classification is also a very futuristic uh, area where people can work who are interested in this kind of research. Yeah. So yeah, that's it. So I'm open to any question. If somebody has question, they can ask.
Okay, 1 minute. I'll unmute the participants so that they can ask queries.
Okay, sure.
Okay, participants, if you have any queries, please feel free to ask. You might know that this is a very interesting application, and Bidisha ma'am has done a very excellent research, and she has like told from top to bottom. So please feel free to ask if you have any queries.